always all the turbines will, the hydraulic turbines will have a small modification in this diagram based on the conditions in which it is operated. Example, for a Pelton wheel turbine, only the velocity is tangential. So V1 will be very horizontal. So alpha is equal to 90 degree and theta is also equal to 90 degree. And V1 is equal to sum of, so the diagram will be shift like this for a Pelton wheel turbine. So the velocity component will be always like this. So output side, there won't be any major changes. So the same be W2, U2, but in input side, the V1, U1, all these terms will be in the same side, and V1 will be equal to VW1 because VW1 is the horizontal component of the blade. So when we look up the previous whole velocity diagram profile, so we say only the horizontal component is there and the vertical components will be become 0, and alpha is equal to 0 and theta is equal to 0. So VF1 is there here and VF1 is not here. This is for a Pelton wheel turbine. Similarly, for a Francis and Kaplan turbine, the velocity diagram will be the slight deviation. So there will be a slight deviation, that they are radial flow. So output, they say there is no radial component, that is V2 will be equal to Vf2, that is Vw2 will be equal to 0. So we will draw it neatly. And the input conditions remain the same velocity triangle of the original plot will be repeated. U1, VW1, V1, sorry, VR1, V1, VF1. Here VF4, VF2 is equal to V2, and we have only the U2 term here and VR2 term here. So VW2 will be equal to 0. So based on that, the impeller power is also modified in the reaction turbine, as impeller power is equal to rho into Q into VW1 U1. That's all. So we have a small, like what it was simplified, and only the theta beta angle will become 90 degree, and phi term will be given. The vane angle is there, so here also vane angle is there, theta, and the blade angle alpha is there. So in the input condition, output condition is almost constant. So only thing which is around here which is going to differ is a Q1. So this small deviation is going to be there for this is for impulse turbine and this is for a Francis turbine. So the Q term is going to be get deferred, that is discharge. So in it is easier to measure the discharge in that inlet area, inlet side, than the output side, because the output it will get scattered too much. So we will be making small assumptions here, which always okay. So here Vf1 is equal to 0, which is already easier. So in inlet side we are saying the jet is having a uniform diameter jet, and it is straight lined. So that is the only assumption we are going to make. So discharge is in terms of the jet water in the jet striking the blade. So here the blade, the water is moving inside the curved area of the blade here. This area will be, we will have the water movement. So for pumps, it will be in the opposite side. The water will be entering here and leaving out in the outer edge, but in turbines into inward flow. So that is also an important term here, playing a major role. So uniform diameter of jet. So we will having the cross section area of jet pi by 4 dj square into velocity of jet is, which is nothing but v1, will give the discharge. So we are saying that it is from a nozzle, so v is equal to root of 2gh. So this is a thermodynamic plane, so we have some efficiency term. For that we will be having a constant called cv, which is a velocity constant. So we can also calculate the u1 relating with the pi term. Pi is nothing but flow ratio. Flow ratio is nothing but velocity of blade by velocity of jet. So with this formulas we can be able to calculate the discharge. So once the discharge is known, we can be able to calculate the various other factors using the just small relations of sin theta, cos theta, and all this stuffs, sorry, beta and phi. So but the discharge Q formula is slightly different in the radial turbine. So when you consider a radial turbine like this, the Francis turbine water will coming into this direction and moving it out in radial direction. So in Francis turbine, the water flows like this. Here the water will be coming in. 1 minute. Water will be coming in the axial direction and flows to the center and moves out like this. So water comes here, goes to the center and moves out. So in this day, the circumference of the blade pi d is a inlet condition. So area of flow is pi d, and the thickness is to be considered, the blade thickness pi d into b into, so velocity is flowing, so vf1 is the flow velocity, because the flow is from the direction of this. So from the external to the center point, the flow will be from the external to the center. So when it consider vf1 will be the flow velocity. So impeller power, the Q will be equal to pi dB into vf1 for the, and the same velocity will be obtained, and the velocity ratio. And here in Francis turbine, v1, u1 and u2 will be very different. u1 is not equal to u2 because the velocity will be, u is nothing but pi d n by 60. So which is nothing, it's just always related with the RPM and the diameter. The diameter here in the center will be a very small one, so the velocity will be small, but at the external side the diameter will be very large, so velocity will be very high. So will be u1 will be greater than u2. So we should calculate the diameter velocity separately, unlike in Francis turbine, unlike in Pelton wheel turbine and Kaplan turbine. While for Kaplan turbine, the guide planes and all this structure will be kept in the top here in this outer region, and water will flow only in the top to bottom, and the propeller shaft will be kept at the center here. The propeller shaft will be get rotated by the water, and the flow energy generation occurs. So the flow direction of flow is like this in the center, but in center we have the shaft which is very large in diameter. So that circular shaft area should be reduced Here it's also a blade will be kept in the Francis turbine, but the blade will be very negligible. Here also the blade is negligible, but the center hub which is very large. So the Francis turbine, the Q will be of formula 5 by 4 d outer square minus dh square. dh is nothing but the hub diameter or the center diameter which is there. So the rest, the discharge formulas and all these procedures will be same, and here the velocity at the instant will be given. The velocity at the water is flowing from top to bottom, so diameter is playing a minor role here. So velocity at point at the top here will be equal to the point at here. So V is the same. So into V of 1 is there. So velocity u1 will be equal to u2. So based on this only assumptions, these assumptions, we can able to solve any kind of turbine problem with this same formulas. Only thing we have to know the equations here.